Chevrolet Cobalt, engineers have found that the miles per gallon in highway driving are normally distributed with a mean of 32 miles per gallon and a standard deviation of 3.5 miles per gallon. What is the probability that one randomly selected Cobalt gets more than 34 miles per gallon? This is part A. Part B, 10 Cobalts are randomly selected and the miles per gallon for each car are recorded. What is the probability that the mean miles per gallon exceeds 34 miles per gallon? 20 Cobalts are randomly selected and the miles per gallon for each car is recorded. What is the probability that the mean miles per gallon exceeds 34 miles per gallon? Would this be unusual? Okay, so let's tackle the first part of this. So we have a distribution. It's a normal distribution. They give us the mean, they give us the standard deviation, and they told us it's normal. So for part A, very easy. We have this guy, it's a normal distribution. So therefore it's got x. Mean is 32. And the standard deviation is 3.5. Okay, so what is the probability that one randomly selected Cobalt car, has more than 34 miles per gallon? Okay, so we want to find 34 right here, and we want to find the area underneath the curve that's to the right of 34, more than 34 miles per gallon. Good. So the answer is the probability that x is greater than 34 is going to be equal to normal CDF from 34 up through infinity, where there's a mean of 32 and a standard deviation of 3.5. So let's find that answer. I'm getting 2839. 0.2839. So that means that back here, this is 28.39%. So two ways to interpret that. The probability that one randomly selected Cobalt car gets more than 34 miles per gallon is 28.39%. On the other hand, of all Cobalt cars produced, approximately 28.39% of those will be vehicles that get more than 34 miles per gallon. Right? So two ways of interpreting the same result. The probability that one is randomly selected or the proportion of all of them. Any questions? Good. So that's good for part A. All right, part B. 10 Cobalts are randomly selected and the miles per gallon for each car are recorded. What is the probability that the mean miles per gallon exceeds 34? Okay, so now we're looking at the mean from a sample. Okay, so we have this situation, we have this sort of parent distribution up here. I know it's normal. I know that the mean is 32, the standard deviation is 3.5. That's random variables x. And I'm going to be taking samples of size what? N equals to 10, right? Because they're talking about the mean from a sample of size 10. So I'm taking samples of size 10. I do this one time. I take 10 random samples. I'm going to get some x bar. Just making stuff up here. Maybe the mean of my first randomly selected sample of size 10, maybe the mean is 33, right? I pick 10 numbers at random from here, and the mean might be 33. You know, I'm just making stuff up here. How about another random sample is selected from this, right? Lots of random numbers are selected from this distribution, and then I find the mean by adding them together and dividing by 10. Maybe this one has a mean of 28.7. Could happen, right? We do that over and over and over and over and over forever. And then we graph all of these, and we are guaranteed that we're going to end up with a normal distribution. Normal distribution of sample means. Right, so this is an X bar there. Any questions so far? No? 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 Okay. So I know that the mean mu sub X bar of this distribution is going to be equal to the mean of that one. So I know that that's going to be 32. And I know that the standard deviation, sigma sub X bar of this distribution, is going to be equal to the standard deviation of that distribution divided by the square root of 10. Right? Following the property from before, it's equal to sigma divided by the square root of n. In this case, n is 10. So let's find that value. 10 to the 0.5 and 3.5 divided by that number is going to be 1.1068. 1.1068. Any questions? No? 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 Okay, so now we're ready to answer the question that they asked us. What is the probability that the mean miles per gallon exceeds 34 miles per gallon of one sample of size 10? So among all these possible random samples of size 10, let's say one of them in here had a mean of 34 miles per gallon. That's possible. Okay, so that means it was one dot in this distribution right here. Here's 34. Okay, so this question is asking me what is the likelihood that I would get a result of 34 or larger. So I gotta go to the more extreme endpoints here and I find that area. Okay, so very important distinction between part A and part B. Part A is saying what is the likelihood that one randomly selected car has a gas mileage of more than 34, whereas this is asking what is the likelihood that when we randomly select 10 cars, the mean of all 10 cars exceeds 34. Right? That's very different. That's not saying that every single car is bigger than 34, that has a gas mileage greater than 34. There might be in the maybe among the 10, maybe there's one that only gets 26 miles per gallon, but then the other ones exceed that, right? Maybe the other ones are so good that the average of all of them is greater than 34 miles per gallon, right? Yes, yes, yes. Good. Everyone clear on the difference between question A and question B? Right? This is a chapter 7 question, right? Very straightforward chapter 7 question, and this is the chapter 8 part. Now we're looking at a sample of a particular size and looking at the probability of getting such a sample. Good? Questions, questions? And we're guaranteed this was going to work, right? Because the parent distribution was normal, right? Because the parent distribution is normal, we're guaranteed that this was going to be a normal distribution of sample means. So we're good. Okay, so now we want to find this area in this distribution then. So the probability that x bar is greater than or equal to 34, so now we're using x bar instead of x, is equal to normal CDF between 34 and infinity. Between 34 and infinity with a mean of 32 and a standard deviation of 1.1068. Okay, so very similar to this one over here. They're both normal CDFs. The limits of the integration, the limits here, the lower bound, the upper bound are the same. The mean is the same. The only thing that's really different is this. Here we used an x, and here we have to use x bar. And here we use 3.5 to be the standard deviation of that distribution. And here we use 1.1068 to be the standard distribution of this guy. Okay? Questions? Questions? No questions. Okay, so let's figure out what that is. Getting 0.03538. Okay, so notice that it's a much smaller likelihood. That makes sense. The odds of getting one randomly selected cobalt car whose gas mileage is greater than 34, 28% chance. Okay, that's just one. The odds of getting 10 of them whose average is greater than 34, well, that's going to be a much more rare thing. Right? Think about like heights. The odds of randomly selecting one human who's tall, okay, let's say above 7 feet. It's hard to find a person that's above 7 feet, right? So the odds of finding one randomly selected person whose height is above 7 feet is small, but it's even more rare to randomly select 10 humans and their average height is above 7 feet. We'd have to have a lot of really tall people. Now, not all of them have to be above 7 feet. We could have one short person in the group, but then the other ones would have to be so much taller that they overcome the height disadvantage of that one person, right? So the mean is above 7 feet. That's more difficult than just finding one individual person that's above 7 feet. Any questions about that? Good. Okay, so then that's part B. Part C says 20 cobalt cards are randomly selected and the miles per gallon of each are recorded. What is the probability that the mean miles per gallon exceeds 34 miles per gallon? Would this be unusual? Okay, so it's a very similar question to this one, except that instead of getting a sample size of 10, we're going to get a sample size of 20, right? So part C, we still have this parent distribution. Sample size is now 20. We are guaranteed that the distribution of sample means is going to be normal because we know that the parent distribution from where they come from is normal. So I'm just going to jump to the end here and go right to here. And I'm going to say that this is a sampling distribution. So this is a normal distribution of sample means. X bar. I know that mu of x bar is still going to be equal to 32, but now what's different is the standard deviation of x bar. So following the formula, it's equal to the standard deviation of the parent distribution, which is going to be equal to 3.5 divided by the square root of 20, because the sample size has changed to 20. So 20 to the 0.5 power, 3.5 divided by that answer. I'm getting 0.7826. Okay, and now they're still asking about that 34. So what is the likelihood that in a sample of size 20, the mean miles per gallon achieved is 34? So now it'll be over here, 34. So it's going to be a very similar statement to that one. The probability that x bar is greater than or equal to 34 will be equal to normal CDF from 34 through positive infinity, where there's a mean of 32 and a standard deviation of 0.7826. Questions? Okay, so let's find that. Distribution. 0.0053. So very small likelihood. About half of 1% chance that one randomly selected sample of size 20 would have an average gas mileage of more than 34 miles per gallon.